Now, this is really our second section that we're going to go into, and this is where we're going to talk about some of the characteristics of ionic compounds and even how to go about writing the formulas for ionic compounds, for binary ionic compounds, I guess we'll say. Now, ionic compounds are some of the ones that we use on a regular basis. What do I mean? Well, outside of table salt, which we use on our food, many of our toothpastes have sodium fluoride. The fluoride in it helps to strengthen our teeth. We deal with a lot of these compounds on a regular basis, but many times we don't actually know how they're formed or where they come from. We just know that they're there. So, ionic compounds are usually going to be composed of cations and anions. So, we talked about cations being the positively charged atoms and anions being the negatively charged atoms. Now, because of this, they're going to have a couple of different properties that we'll be able to observe and sort of look at over the next couple of days. Now, first property, they're going to be electrically neutral, or they have a net charge of 0. They're going to cancel out each other's positive and negative charges to be 0. They're usually going to be crystalline solids, or crystals at room temperature. So if you look at the grains of salt, usually kind of feel rough as you touch them. They have very high melting points and conduct electricity when melted or dissolved in water. And we're going to do a little demonstration of that to be able to determine whether things are ionic or whether they're covalent compounds. We'll talk about covalent next time though. Now, what actually holds these ionic bonds or ionic compounds together? They're held together by what we call ionic bonds, but that's basically just electrostatic forces holding the ions together. Electrostatic forces, a nice way of saying I have a positive, I have a negative. We know that opposite charges attract each other, so because they're oppositely charged, they're stuck together. Makes perfect sense. Now, if we're looking at the diagram here, we see that sodium is transferring, or actually giving away, that electron to chlorine. So remember when we talked about sodium giving away an electron and chlorine gaining one? If you're wondering where in the world that electron comes from, it's usually given one to the next. This is going to allow them to have what looks like a full octet and to become more stable, and they'll be stuck together because of it. Now, when we write ionic compounds, we have to write them in terms of a chemical formula, which is going to show the kinds of elements and the number of those atoms or elements that are there in the smallest representative unit. And we call this a formula unit. So usually when we deal with ionic compounds, you'll note that I won't say molecules. There's a good reason for that. But the formula unit is going to be the lowest whole number ratio of the ions in an ionic compound. Now, this type of compound that we're going to start with first is what we're going to call a binary compound. Binary, like bicycle, is going to be is composed of 2 elements. Now, binary compounds can be ionic or molecular, but in this case we're dealing and focusing on the ionic. Sorry about that. Now, if you know the name of the bionic compound, you can write the formula. If we know the 2 elements that are involved, most times we can write the formula. Now, to write the formula of a binary ionic compound, first we write the symbol for the cation. Cation always goes first. Then we write for the anion. Then we add subscripts to sort of balance it out. In the end, again, we talked about the fact that it has to equal or have a net charge of, sorry, my writing is bad, of 0. This is very, very important when we deal with our ionic compounds. It cannot be otherwise. So, the way that we're going to go about doing this is we use something called the crisscross method. We practiced a little bit writing the ion symbols for each of the elements. So we're actually going to go about using that to solve this. So if I have iron with a 3+ charge, as we see here, and I have oxygen with a 2- charge, what I'm going to do is I'm going to take the number, not the charge, just the number, and I'm going to crisscross it. The charge, the number from the charge, is going to become the subscript for the other ion. So, as we see here, if I have Fe3+ and O2-, when I use my crisscross method, I'm going to end up with Fe2O3 because 2 times 3 would give me 6, and 3 times 2 would give me 6. Adding that up, negative 6 plus positive 6 will give me 0, which is what my goal is in the first place. Now, if we happen to use the crisscross method to write the formula, and we have two things that have the same charge, or same magnitude of charge, what do I mean? So we have calcium and sulfide ion, right? When we put them together, if we use the crisscross method, we notice that plus 2 will be Ca2S2. Now, is that the lowest whole number ratio? No, because calcium has 2 electrons to give away, and sulfur is going to accept those 2. So we just reduce it down to CaS, which is what we see here. Now, this will be the lowest whole number ratio. And again, we're going to do a little bit more practice with this, where you're seeing what's happening with the Lewis structures. So it makes it a little bit more clear what's happening overall in the forming in the bond. Again, the overall charge, 0. Make sure you have that part taken care of. Now, if we're using the example of a metal, sorry, another example given of how to actually name these compounds now. Well, we talked about how to name the ions before, right? This part, I believe, is actually going to become kind of easy. Because I have a compound that's going to be made of cesium and oxygen, composed of metal, non-metal. Remember, the metal name in the ion was, say, cesium ion, right? So we're going to keep that part. We're going to keep the cesium. We're going to drop the word ion. Now for oxygen, we had an oxide ion. We're going to drop the word ion, but now we're going to keep the oxide. So the name of the compound overall that we're looking at is cesium oxide. Same way as dealing with here. We had a sodium ion with a bromide ion. When we put them together, we just drop the words ion and get sodium bromide, or strontium fluoride. My hope is that you're starting to see the pattern of how these sort of work out. It's not very difficult. It's something that we should be able to pick up. But if you're having issues, make sure you ask questions. Don't just wait until we get to a test or a quiz and things aren't making sense. Ask questions immediately. Now, if we're dealing with a transition metal, which is the ones we talked about having more than one common ionic charge, we have to include, just like we did before, the Roman numeral saying the charge in the name. So, if I'm looking at, let's see if I can get it to work. If I have iron, there we go, iron 3 plus, and chlorine, or chloride ion, it's going to form FeCl3, or it's going to be iron 3, 1, 2, 3, chloride. I cannot write for a transition metal the name without including that Roman numeral. It has to be there. Now, we looked at this part before, and so I just want to give an idea of how this is actually going to form. Remember I talked about the fact that we form these crystals with these ionic compounds. Well, what you see in the diagram here is we have a chloride ion is taking on this extra electron, whereas sodium is given away, and because of that they have these charges. Now, these charges don't just go in one direction. So if I have a chloride ion here, you notice that there's a sodium ion attached to it here, attached to it here, and attached from that side. Same thing is repeating the whole way through. This is the reason why we end up with this crystalline structure, because of how they end up bonded together, very close together. It actually forms sort of a box, a continual building structure. Similar thing is we take these different compounds, these different substances. Ooh, I actually want to go back, because in my mind I'm thinking, well, sodium metal, when you put sodium metal in water, it actually explodes. Chlorine gas, which is how we normally find chlorine, it actually can kill you. But when we put these two things together, we get this, which is what we're used to actually seeing and dealing with. That being the case, when we form ionic compounds, it's going to change the structure and the properties many times of the compound. Same thing as what we're seeing here. I have bromine, which is a liquid gas substance at room temperature, and aluminum, which many times we use as foil. When I put the two together, I end up with this crystalline solid, aluminum bromide. So we're going to look at how these will sort of be changed just a little bit. Now, if we were to give this example, it says use electron dot structures to predict the formula of the ionic compound of the following elements. Let's take a look. I have potassium and oxygen. Well, potassium, I have 1 valence electron, and oxygen, I have 6. Now, when I put those together, I'm going to find that if I only focus on this one, then I only have 1 to donate, right? But if I add another potassium, I can help this oxygen reach its full octet. So I'm going to end up with a formula that looks like this is potassium oxide. Now, this seems like we went kind of fast in this part, but please do not worry. We're going to take some time in class. Have a good one, and we'll begin the next unit another day.